Good afternoon, students. We discussed regarding the chemistry in everyday life in the last class. Today we are going to start polymers. What are polymers? Polymers are the macromolecules, those macromolecules which are having a repeating unit continuously, then we are going to call that one as polymer. But we are going to have the polymer and macromolecule, a difference will be there. So when we are going to take polymer, that should consist of at least one or two are going to be repeating in that a compound. They are called as polymer, and that repeating unit is called as monomer. But the macromolecules are going to be the one which is going to have large in size. They are going to have huge molecular weight, but they are not going to have a repeating unit. A repeating unit is not going to be present. Say for example, chlorophyll. Chlorophyll is a giant molecule. It is going to have huge molecular weight, but that is not going to have any repeating unit. It's a broad structure. So that cannot be called as polymer. Just know this difference. Whenever they are asking which of the following is polymer, which of the following is macromolecule, we are supposed to see that is going to be consisting of any monomeric unit in it. Say for example, protein. The protein is a polymer of amino acid. So if you can able to see any particular protein, that is going to be having a repeating unit of those 20 standard amino acids what we discussed already. If you are taking starch, starch is going to be a polymer of alpha D glucose molecule. When we are going to take this starch, it is going to be consisting of the glucose molecule is going to be repeating. So glucose is called as monomer, your starch is called as polymer. Similarly, we are going to have so many polymers we discussed already. All polysaccharides are examples for polymers only. Now, when we are going to take a molecule like chlorophyll, I said, or cytochromes we are having, these are all the substances, they are going to have huge molecular weight, they are giant molecule, but they are not considered as polymers. That's why remember, which of the following is macromolecule means which is not having any repeating unit. Which of the following is polymer means which should have one repeating unit. Now what definition you can equal to give? A giant molecule which is made up of the repetition of a single molecule, that is called as polymer. The molecule which is going to be repeating, that is called as monomer. This is about the polymers. In our regular life, we are going to have so many polymers we are using. Everything, whatever you are using it, that comes under polymers only, many of the things. PVC, the plastic what you are going to use for so many purposes. And you are going to have polystyrene, polyester cloths we are using. So many are there. Melamine, plastic. So these are all comes under polymers. We are supposed to learn the polymers in depth. So first we will see the classification of polymers. How we are going to classify a polymer, that we will see first. Fine. What is the classification you are having? The first classification based on source. Based on source, I will take the first classification. Based on source, if you are taking, I am going to have natural polymers, synthetic polymer, semi-synthetic polymer. What we are going to have here? We are having total 3 types of polymers, that is natural, synthetic, semi-synthetic. What are natural polymers? Natural polymers are the polymers which are going to be obtained from a natural source. What they are? They are going to be obtained from a natural source. They are called as natural polymers. Say for example, we are having so many examples. Polysaccharides Already we discussed so many things about them. Examples I am writing here. Polysaccharides, proteins, lipids, nucleic acids, what else? They are all comes under your natural polymer. These natural polymers are going to be formed from a natural source. As we know that polysaccharides are going to be present in living organism. They are going to be useful for giving us energy, and cellulose is going to provide a cell wall strength. They are going to be, proteins are going to have so many functions we discussed, hormones, enzymes, everything is protein only. And lipids, they are going to be lipid bilayer for membrane, and bio-NC is also maintained by lipids. Nucleic acid, DNA, RNA, they are the polymers of nucleotide. Nucleotide is the monomer, nucleic acid is a polymer. And we are going to take lipids, they are also going to be polychains, fatty acids are going to be making these lipids. And we are going to take protein, they are made up of amino acids. When we are going to take polysaccharides, they are going to be, a monosaccharide will be glucose or fructose or something is going to be present. So they are all derived from natural sources. When we are going to take synthetic polymers, synthetic polymers are nothing but which are synthesized in a laboratory. Which are synthesized in a laboratory. The polymers which are synthesized in a laboratory are going to be called as synthetic polymers. All the man-made polymers comes under synthetic only. Examples: PVC, polythene, all plastics, whatever it is going to be comes under the laboratory synthesis. They are all will be the examples for your synthetic polymer. Semi-synthetic, they are having synthesized by a man, but the source for that one is taken from the natural one. They are going to be naturally obtained raw material can be converting into a polymer, that is called as semi-synthetic. It is not it is not completely synthetic, it is partially synthetic because it is going to take some natural source, then they are going to make this polymer. That's why they are called as semi-synthetic polymers. Examples for semi-synthetic polymers are rayon. Is nothing but cellulose acetate. It is also called as artificial silk. It is looking like silk, but it is going to be synthesized by a man. It's an artificial silk we are going to call rayon. It's nothing but cellulose acetate. It is going to be cellulose acetate will be an example for how we are going to take this one. It's a wood pulp. How we are going to take the wood pulp? So that wood pulp is going to give you the semi-synthetic polymer, and we are also having cellulose resin. Cellulose nitrate. They are all the derivatives of your cellulose. Their cellulose is going to be get modified. That modification is going to give you a polymer. That's why they all comes under semi-synthetic polymers. So this is what the first classification you are having for the polymers, that is natural, synthetic, semi-synthetic. This is what we are having. And next, coming to the classification based on, we can take structure. Based on structure, we can take, here we can have three types: linear, branched, cross-linked. We are going to have three types of classes will be present based on the structure of polymer. So first one is linear polymer. So what is linear polymer? The polymer is going to be having existence in a linear structure. They are having the linear structure. So the linear structure of polymer is going to be giving by the monomeric units which are arranged in a linear fashion. Say for example, if you are having, this is how we are going to have the linear polymers. They are completely polymerization of linear type. So when we are going to have the structure of that polymer, it is going to be comes under linear fashion. They are going to be polymerized. That's why you are going to get high density. Whenever you are going to have close packing, they can able to get high density, high tensile strength. All you are having the linear polymer, it is going to be having high density. They are going to have high density, high tensile strength. Usually we are going to have nylons and polyesters. Usually we are having nylons and polyesters will be comes under this one. Understand? Nylons and polyesters, and you can able to take polythene, high density polythene. High density polythene, HDPE. High density polythene, and we are going to have nylons and polyesters can be comes under linear. Why? Because they are going to be arranged in a linear fashion and they are going to be get attached to parallel to one another. That is going to be called as linear polymer. And branched polymer, they are having some other functional groups, middle, like this they are going to be. So middle, we can have some cross links. It's not cross link, it just is going to have some functional groups are executing so that they can able to show the branching. Say for example, amylopectin. We are going to have amylopectin, glycogen, and LDPE, low density polythene. Because of these branches, they can't able to compactly packed. As they are not compactly packed, they are not able to get more density. They can able to have low density, low tensile strength. Low density, low tensile strength. That's why they are going to have the softy nature. Amylopectin, glycogen, low density polythene. They are comes under examples of branched polymers. Now coming to the cross-linked polymer. Here we can able to say bakelite and all. So the chains are going to be forming a cross links between them so that they are going to get more hardness, more brittleness. So they are going to be called as cross-linking polymers. Example you can take bakelite, melamine formaldehyde resin. Melamine formaldehyde resin, bakelite will be comes under your cross-linked polymers. When we are going to take this classification based on the structure, we are going to have three types of classification. First one is linear polymer, second one is branched polymer, third one you are having cross-linked polymer. When you are going to take linear polymer, all this polymerization is going to be taking place in a linear fashion and they are going to be arranged very compactly, closely. That's why they can able to attain more density, more tensile strength. They are going to be very strong, very rigid. That's why they are going to be examples. High density polythene, nylon and polyesters will be the example. And when you are taking the branched polymer, they are going to have some functional groups are going to be present in this polymeric chain and they are going to make the not closely packing. So because of this not closely packing, they are not able to get more density. That's why they are going to get low density, low tensile strength, and the modulus is also less. We are going to compare with a linear polymer. And they are going to be having low density polythene, amylopectin, glycogen will be the examples for them. Then next we are having cross-linked polymer. The cross-linked polymer when you are taking, they are going to have the linear polymers, but we will be having some branching can be making them to get attached to one another so that they are going to get more. Usually the cross-linked polymers are going to be a multifunctional group monomers will be present. Bifunctional or trifunctional monomers will be present. So these monomers, when they are undergoing polymerization, they will be able to make this cross-linking polymer. They are able to make cross-linking polymer. So they are also having a huge strength. Once they are getting the cross-linking, they will become so rigid. So they are going to be resist for many things. Bakelite and melamine formaldehyde resin, the unbreakable crockery is going to be made by these things only. So that is the best example we are having, the cross-linking polymer. And next classification we are going to have based on intermolecular forces. What is intermolecular force? We are going to have. What will be the intermolecular forces we can have? Based on intermolecular forces. IMF or interparticular forces. We can call them as intermolecular forces or we can call them as interparticle forces. When we are going to take intermolecular forces for a polymer, what forces we can able to expect? What forces we can able to expect? One is obviously van der Waals forces. One is going to be van der Waals force. Another one you can able to get intermolecular forces, hydrogen bond, or you can have ionic forces. So that is the forces we can have based on the percentage of intermolecular forces. We can able to classify these polymers into elastomers, fibers, thermoplastics, thermosettings. So what the four we are going to have? Thermoplastics, thermosettings and fibers and elastomers. These are the four classes we are going to have in this. When we are going to take elastomers, fibers we can able to write. Elastomers, the first one. So what are elastomers? Elastomers, the name itself is going to say it's going to have elasticity. We are going to have elasticity. What do you mean by elasticity? When we are going to stretch that one, it will be get stretched. When we are going to leave the force, it will be coming to its original state. Elasticity, what it is? When you are going to apply the force, they will stretch. When you are leaving the force, they will come back to their original state. That's called elasticity. Those polymers which are showing elasticity, they are comes under elastomers. When we can able to get this elasticity property for your polymer? When we are going to get? Whenever we are having weak intermolecular forces. When we are having weak intermolecular forces, whenever you are applying the stretching force, that forces are going to be get broken easily and they will be get stretched. The polymers are actually closely packed. Now when you are applying the stretching force, those forces which are present in between, they are not going to be making the force against. That's why they will be get stretched. Whenever you are leaving the force, again they can able to establish those forces and they will be regaining their structure. So that is what we are going to have, elastomers. Elastomers are nothing but the polymers which shows the less intermolecular forces due to which they can show the property called elasticity. What is elasticity? When we are applying the force, that forces will break down. When we are relieving the force, they will regain their original structure by reconstructing the forces among the polymeric chains. So all rubbers are going to become the examples here. Biona N, Biona S, natural rubber, whatever the rubbers we are having, all of them will be comes under your elastomers only. We are going to get in elastomers. Next, fibers. Fibers are the polymeric chains which are going to have much more intermolecular forces. These intermolecular forces are going to provide a more modulus and more tensile strength for your particular polymer. Say for example, when we are going to take nylon 66, nylon 66 is going to be having CONH, which is similar to your peptide bond. How we are going to have the protein tertiary structure or secondary structure? These CONH are going to form hydrogen bond between them. So that hydrogen bond is going to make your particular hydrogen bonding strength for that particular protein. In the same way, nylon 66 is also a polyamide that is going to have CONH. How we are going to get this one? It is made up of, example, it's going to be nylon 66. How it is made? COOH, CH2 4 times, COOH plus H2N, CH2 6 times NH2. Here 6 carbons, here 6 carbons. That's why the name is given nylon 66. Now they are going to be get polymerized, like here hydrogen, here OH will be removed and they are going to form now, when we are going to have this one more chain, so there is a possibility of getting like this. It can able to form like this. So this is the extension we are going to have. There is a possibility of showing hydrogen bond between the O of one carbonyl group to hydrogen of another one. Here also hydrogen for this one to CO this one. So there is a chance of getting a intermolecular hydrogen bonding in the case of fibers nylon 66. That's why they are going to get high tensile strength. Hydrogen bond is always going to have 10 kilojoules per mole of energy. So that much tensile strength can be developed by these fibers. Examples, if you are taking nylon 66 and all fibers, whatever you are going to have the polyesters, dacron, silk, everything is going to be comes under this one only. Polyesters, polyamides always are going to have the chance of getting intermolecular hydrogen bonding. That's why they will be comes under fibers. Next, coming to the thermoplastics. Thermoplastics are going to have intermediate molecular forces between elastomers and fibers. How much intermolecular force are there for elastomers and how much intermolecular force is there for fibers? In between, they will be showing their intermolecular forces. So always you are going to get the question, what will be the order of intermolecular forces among the given order? So they will give one example for thermoplastic, they will give one example for elastomer, they will give one example for fiber. Then what the order you are supposed to follow? Fibers are greater than thermoplastics, thermoplastics are greater than elastomers. Otherwise they will give directly example. Arrange the following in increasing intermolecular forces. Nylon 66, one rubber, that is Biona and one plastic PVC. Now which one is going to have more? Fibers. That's why nylon 66 is greater than thermoplastic PVC, greater than here Biona or Biona rubber what they given. So it is a way they can able to ask the arrange the following in increasing or decreasing intermolecular forces. This is the way we can able to give that. Understand? Now coming to the thermoplastics. how they are going to be acting. They will have, I said, the intermediate intermolecular forces to your fibers and elastomers. Now, whenever you are going to apply the heat, they will become liquid. They will become soft. Whenever you are making them to cool, again they will become hard. So, there is a continuous cooling and heating is making them soft and hard. Soft and hard. That is the one they are going to be thermoplastics. The examples we are having is PVC, polythene, all these things are comes under thermoplastics. And the last one, thermo settings. Bakelite, melamine formaldehyde resin. So what they are going to do, melamine and bakelite, they are going to make the difference between the thermoplastic and thermosetting. Thermosettings are those polymers when they are going to be settled down once, they will never reusable, they will not come back again. But in the case of this one, once they are going to be get heated, they will become cool. When they are getting, when they are going to be get heated, they will become soft. When they are cooled, then they will become hard. Again, we are heating it, it will become soft. That is the one we are going to see in case of thermoplastic. But once they are going to make cool, they will be settled down. But after that, they will never come back to on heating also liquefy. That is what we are going to have thermosettings and thermoplastic. Why they are not coming back again? Because of once they settle down, they are going to establish the cross-linking. They will establish the cross-linking. Those cross-linkings can't be break by a heat. So we can't able to reuse the thermosettings, but I can able to reusable thermoplastics. Understand? So this is what the classification based on their intermolecular forces. Their intermolecular forces are going to have elastomers, fibers, thermoplastic, thermosettings. Example for elastomers are bunion, so all rubbers will come. For fibers, we are having nylon 66, dacron or polyesters, we are going to have all they are going to establish that one. Then we are taking thermoplastics, we are going to have PVC and polythene, they are going to be reusable. Thermosettings are going to be bakelite and melamine, they are not reusable. That is what we are going to have the polymers classification based on their intermolecular forces. The next classification I am going to take based on composition, based on their composition. So what we can able to observe the composition is going to explain whether it is going to be made by a single monomer or whether it is made by more than one monomer. That is what we can have. So we can able to call based on monomeric unit, we can say monomer composition. This is fourth classification. We have seen already three classifications. Now this is the fourth classification based on monomer composition. I can say homopolymer, copolymer. Homopolymer, copolymer. So many times they are asking which of the following is homopolymer, which of the following is copolymer. Homopolymer means a single monomer. They are made up of single monomer. Copolymer means two, alternatively. We are going to have alternatively two monomers are going to be forming a polymer. It's called as copolymer. If we are going to have a single monomeric unit is repeating continuously, we are going to call it as homopolymer. Homopolymer, copolymer. That is, they are going to ask which of the following is copolymer, which of the following is homopolymer. We are supposed to see the composition what they given. It is going to be consisting of a single molecule. It's a homopolymer. If it is made up of many, then we are going to have many means two. We are going to be get alternatively one another, one another, one another. It's called as copolymer. That is what we are having the classification based on the monomeric composition. And the fifth one is an important one. based on mechanism. Based on mechanism, we can have two types of polymerizations: addition polymerization, condensation polymerization. We are going to have two types of polymerizations: addition polymerization, condensation polymerization. Addition polymerization is also called as chain growth polymerization. Condensation polymerization is called as step growth polymerization. So it is called as addition polymerization or chain growth polymerization. It is called as condensation polymerization or step growth polymerization. So this is going to be depending upon whenever we are going to take addition polymerization, that is commonly require an unsaturation. So that is multiple bonded monomeric units whenever we are having, they will undergo addition or chain growth. When we are going to have condensation, when a small molecule is removed for making the combination of two monomeric units, it's called as condensation. So what is addition polymerization? Without any loss. We are not having any loss of anything, just we are adding up the things. Then it is called as addition polymer. Say for example, CH2 double bond CH2. N molecules are taken and this is going to give CH2, CH2, N times. So nothing was lost. What I am taking CH2 double bond CH2, the same thing is going to be get polymerized. We got CH2, CH2 N times. It's an ethylene molecule. It's going to be polythene molecule. And now we are taking like condensation polymerization. Here, say for example, earlier only we discussed nylon 6,6. What is going to be happen here? Here it is lost, the water molecule. What is condensation? We are going to condense something. We are going to condense something that is going to make the combination of two monomeric units. Then we are going to call that polymer as condensation polymer or step growth polymer. Why it is called step growth? Why it is called as chain growth? When we are going to take addition polymerization, the growth of polymeric chain will be in the form of chains. When we are going to take step growth polymer, the growth of the polymeric chain will be stepwise. That means we can be able to control the growth of that polymeric chain by making some steps are going to be controlled. Whereas in chain growth polymerization or addition polymerization, it is going to be continuously, it is going to elongate that one. We never able to control that polymeric chain length. That's why it is called as addition polymerization as chain growth polymerization and the condensation polymerization as step growth polymerization. And coming to the addition polymerization, we can have three mechanisms based on which is going to be the intermediate: free radical, cationic, anionic. So that is the intermediate which you are going to have. If it's a free radical, is called as free radical addition polymerization or cationic addition polymerization or anionic addition polymerization. Like that we are going to have different types. We will see the mechanisms how the polymerization is going to take place in a given compound. So when we are going to take the addition polymerization, so that addition polymerization is going to have three types of mechanisms I said. So first one we will see the free radical mechanism. So free radical addition polymerization. So it is going to have three steps: initiation, propagation and termination. So how the initiation is going to take place Always a free radical mechanism we require, one free radical should be there. So usual free radical initiation is going to be done by using benzoyl peroxide. What we are having? Benzoyl peroxide. So it is going to have C double bond O, CO, C. This is called benzoyl peroxide. This benzoyl peroxide, not only this peroxide, any peroxide is going to have the weak peroxy bond. So that peroxy bond only will get broken and we are going to get C6H5COO free radical. Now this COO free radical, oxygen with free radical is unstable. That's why this is going to take up the electron from this one and one electron is going to move like this. So I am going to get finally C6H5 free radical. We are going to get C6H5 free radical and CO2. So now the formed C6H5 free radical is going to make the attack on this phenyl free radical, which is highly unstable. So it is going to attack directly on the carbon. So now this one electron is shifted here and this is going to shift like this. We are going to get C6H5CH2CH2 free radical. Now this is going to be added up N molecules of CH2 double bond CH2, which is nothing but propagation. So I am going to get C6H5CH2CH2 N times I can write it. Here I am going to get one CH2 free radical. So these are all comes under propagation steps. Now how to get termination for your peroxide, that is free radical mechanism. Whenever a free radical is present in a given reaction mixture, that will never come to an end, that will never come to termination. When it is going to be get terminated? When we are going to take out this one, then only it is going to be get terminated. So this is called propagation. And the next one we are having termination. How the termination is taking place? We are supposed to have the two free radicals should combine. I am taking one more like same thing here. C6H5CH2CH2 N times CH2 free radical. Now this free radical when they are combined, then they are going to give C6H5CH2 N times CH2. Here they are going to form the bond. Two such rings are going to be, not rings, two such chains are going to be get combined and free radical is going to be taken out from the reaction mixer. So that is going to be a termination step for your free radical addition polymerization. So what you are going to have in this free radical addition polymerization? It is going to have three steps: initiation, propagation, termination. How it is going to be get initiated? Any free radical mechanism should be initiated by helper. We are going to have heat or light or electricity, or you are having peroxide or a radical. So we are taking here benzoyl peroxide is the best one. We are going to have the initiation for the free radical mechanism. The benzoyl peroxide is going to have the peroxy bond. That peroxy bond is going to be get lysed. We are going to get C6H5COO free radical, benzoyl free radical. This benzoyl free radical is unstable, it is going to give CO2 molecule and we are going to get C6H5 phenyl free radical, which is highly reactive. That highly reactive free radical is going to be attacking on ethylene molecule. Now it is going to be get homolytic cleavage and we are going to get free radical on the CH2. Now it is going to be keep on adding the n number of molecules of ethylene and finally I am going to get a stretch of chain with a free radical. It's continuously going to be get added up. But when we are going to get termination, two such polymeric chains which are formed can able to combine with one another, then I can able to make a termination so that the free radical will be get removed from the mixer. So that is how I can able to get free radical addition mechanism, in which I can able to form most of the polythene, polypropylene, all these compounds are going to be formed in addition polymerization only. That will be including free radical polymerization. Polythene is the best example we are going to have for this addition polymerization. The next one we are going to have cationic mechanism. Next one is cationic addition. When the cationic addition is going to be possible, always it is going to be polyvinyl compounds. When we are going to get this polymerization can take place. So always we require an initiation. Initiations are nothing but Lewis acids, that is electron deficient compounds like BF3, AlCl3, SnCl2, etc. When these Lewis acids are present in a reaction mixer, they are going to initiate cationic addition polymerization. They are nothing but polyvinyl compounds we are going to have. How they are going to make this one? Say for example, AlCl3 is there. It is going to be acting on water. So now it is going to be forming AlCl3 OH minus plus H plus. Is going to form H plus. Now this H plus is going to be attacking on RCH double bond CH2, a polyvinyl compound is taken. Now what is going to be formed here? This is going to be getting attached like this. The carbocation is going to be stable here. That's why I am going to get like this. Now this cationic polymerization is going to be mediated by the Lewis acids like BF3, AlCl3, SnCl2. Say for example, if they are given ethene only, polythene if you are taking, ethylene molecule in presence of peroxide, it will undergo free radical mechanism. The same polythene in presence of this, it will undergo the cationic polymerization. The same thing can be having anionic polymerization. For that we are supposed to have bases. There are Lewis acids, in presence of a base they will undergo anionic polymerization. So it depends upon what type of polymerization is the initiator what you are having. If a peroxide is initiating, that will go for free radical. If a Lewis acid like BF3, AlCl3, SnCl2 is initiating, it will comes under cationic polymerization. If a base like sodamide is initiating, then we are going to get anionic polymerization. How that anionic polymerization is taking place, we will see the mechanism now. Next one is anionic addition polymerization. So how we are having Lewis acid for your cationic polymerization? Same way we require an base. Say for example NaNH2, sodamide, or we can take alkyl lithium, RLI. Such bases are present, they are going to bring anionic polymerization. Here also we are going to have polyvinyl compounds, but it is going to be more electronegative atom. Say for example CH2, CHCl. The Cl is more electron withdrawing group. So in that case we are going to have anionic polymerization. Or you can have vinyl cyanide, CH2 double bond CHCN. There we are having cyanide, that is also going to be more electronegative. So that is also bringing anionic polymerization. So this is the favorable conditions, polyvinyl only. But when we are going to have more electronegative atom present in that monomeric unit, they will undergo the polymerization by anionic. That's what we are going to have in this. The one we are having NaNH2, it is going to give like NH2 minus. Amide is going to be attacking on a monomer. So when it is going to be attacking on monomer, so we are going to get MnH2 minus. We are going to have MnH2 minus. Now this MnH2 minus, we are going to have, this is going to be initiation, we can say. This is going to be initiation. Okay, better minus showing on minus of monomer. This is better. So NH2 M minus, that minus is attacking on monomer. Now negatively charged monomeric unit was started. Now it is going to be anion. So this anion is going to be going for propagation. This is going to be propagation. How it is going to be happen? Now this NH2 M minus is attacking on another monomeric units. Say for example, if I am taking N minus 1 number of monomeric unit, so now I am going to get NH2 Mn minus. We are going to get the number of monomeric units are going to be added up like this, and I am going to get Mn minus at the last. Okay, otherwise we will write it like M minus. That minus charge is going to be carried out continuously, so that I am going to have a living polymer. Always we are going to call the anionic polymerization, there is no propagation. It is going to be continuously get polymerized only. That's why this polymer which is obtained by anionic polymerization can be called as living polymer. Why? Because it will never have the termination. It is always continuously going to be get polymerized. That's it is going to be called as living polymer. So this is about your anionic polymerization. Here also polyvinylic only. I said what we are going to have as an initiator, that is going to decide. So many times they are going to be asking the question like, so which of the following polymerization will undergo by ethylene in presence of sodamide? So what it is going to be? Anionic. In presence of peroxide, it is free radical. In presence of a Lewis acid like AlCl3, it is going to be cationic. So the polymerization is depending upon what initiator is present in a given mixer, that is going to decide what type of polymerization can be taking place by your given compound. And we are having several examples for which are undergoing free radical, which are undergoing cationic, which are undergoing anionic. So just I will display the table, then we will discuss. You are supposed to remember them. So these are the examples, we are supposed to remember them. Which of the following is undergoing free radical, which of the following is cationic, which of the following is anionic. That is can be explained by this table. Just you can take a screenshot or you can able to copy into your notebook, but you are supposed to remember them. It depends upon already what we explained the mechanism only. If you are taking styrene, it can undergo free radical, it can undergo cationic, it can undergo anionic. All the polymerization can be takes place by styrene. Any diene if you are taking, dienes can undergo free radical and cationic, but they are not willing to show anionic addition polymerization. And when you are taking vinyl chloride, it will be able to show free radical addition. We are going to show free radical addition polymerization can be shown by your vinyl chloride, and it is not willing to show these two polymerization, cationic and anionic. Then you are taking ethylene molecule, it can able to undergo free radical polymerization, addition polymerization, and anionic addition polymerization, not willing to show cationic. Isobutylene if you are taking, it is going to show free radical and cationic is not willing, but it can able to show the cationic polymerization. When you are taking acrylonitrile, it can able to show the first two, the free radical and cationic addition polymerization, but not able to show anionic addition polymerization. And vinyl esters we are having, only they will show free radical addition polymerization, they are not willing to show cationic and anionic. And vinyl ethers are there, they can able to show only anionic polymerization, they are not willing to show this free radical and cationic. Anyway, they are going to give the initiator what you are going to use for a particular thing, then that is going to decide what type of polymerization they will undergo. That's what the main point we are supposed to take. Any Lewis acid is there, it will undergo cationic. Any NaNH2 like base is there, it is going to be undergoing anionic. If a free radical peroxides or heat is going to be applied, then we are going to get free radical addition polymerization. And condensation polymerization, I already said it is going to be step growth polymerization. In coming to addition polymerization, we are not having the control on chain growth, that's what it is called as chain growth polymerization. But as step growth polymerization, we can able to control stepwise. First, we are going to have one monomer is taken, it is going to form a bond, then we are going to add one more monomer. So like that we are going to get stepwise polymerization is possible. We can able to control the growth of polymer in case of the condensation polymerization, that's what is called as step growth. Nylon 66. Anyway, we are going to discuss many number of polymers, how they are going to be having the monomer and their role, like what function they are going to have. They are going to be given as a table. So that's why we will see all the polymers which are there in our NCERT, we are going to read them. And one more classification we are having, that is biodegradable and non-biodegradable. What are biodegradable polymers? The polymers which are going to be degraded by microorganisms, they are called as biodegradable. The polymers which are not able to degrade by microorganisms, they are called as non-biodegradable. What will be the example for biodegradable? PHBV, nylon to nylon 6. What are non-biodegradable? All your synthetic polymers. Anyway, we are going to study them. Biodegradable, their preparation and everything. At that time we can see. So this is what we are going to have, the classification of polymers. Tomorrow we are going to see how the polymers are going to be having their monomeric unit, their structure and their functions. The other things we are supposed to see, that we will see in tomorrow's class. Thank you everyone. So just go through what examples we given for each and everyone. Then you will see whatever the doubts you are having, you can able to ask me in the interaction session.